are here to talk about sparsification recipes in PyTorch. So the first place I like to start is, what is sparsification? So as many or all of us are aware, as deep learning has grown and the models capabilities with it have, so have the models. The models are getting very large, lots of parameters, lots of disk space that they take up, and to the point where they're almost over parameterized, where we don't fully understand always, what they're learning, is this too much and why are they learning that way? So sparsification is just the process of removing this redundant, over parameterized information from a model. There's many ways of achieving it, but the two ways we're going to focus on today are pruning and quantization. So if you've been to any of our talks before, you're probably well aware that pruning is the process of removing individual weights or nodes from a neural network so that the weights in the multiplication between them become sparse. We're actually able to prune, in most large neural networks, up to 80 to 90, even more % of the weights with very little impact on the accuracy. So what's good about this is, one, we can compress the models down with sparsity, but two, we can also run with sparse operations speed up. And then two is quantization. So neural networks are generally stored at FP32 or 32 bits of floating point information. What researchers have found is that we actually don't need this high level of precision to accurately perform inferences with neural networks. So for quantization, we target in-8 quantization, where we take the FP32 down to 8 bits of integer information. But researchers have pushed this even further with binary neural networks that use 2 bits and still retain high accuracy. But with 8-bit quantization, we're generally able to reduce the number of bits by 4x while retaining most of the accuracy. So obviously this has a theoretical maximum of 4x speed up. In practice, we can see 3 to almost 4x speed up off of this. And what's really exciting that we've been working on is the combination of pruning and quantization to create what we call sparse quantized models. So what we're going to get into is how we can make these apply sparsification to models easily in PyTorch. Great. So we'll move on to the next slide.
Ben, real quick, we had a question that came in about how do we turn zeros into no ops for faster inference? So maybe if you want to dive into that a bit.
Yeah, definitely. So, right. So one thing that this question points out very well is that when we're pruning, we're not actually removing any necessary operation from the matrix representation. We're turning a weight into 0. So this turns the matrix sparse. So for at runtime, how do we do this? Out of the box, inference engines like PyTorch don't for sparse operational matrices, but we have our own product called the deep sparse engine that can detect when there's sparsity in a layer and then run it at and run either like a sparse convolution or a sparse matrix multiplication. So after a model is exported sparse, it can be run with the deep sparse engine to take advantage of the sparsity induced in the model. Great. So moving on. Right. So why is this useful? So as I was talking about with models getting larger and larger, they also get more powerful, right? So engineers want to be able to deploy these models in a variety of settings. This can be anywhere from a large server on a data center to a device on the edge or something on your phone. But the issue is these models can't always run efficiently in hardware constrained environments, and often require large GPUs to run and serve. So as an example, Resident 50, one of a very popular image classification model, to run on a 4-core CPU, it's come quite a long way. A few years ago, it took maybe a couple hundred milliseconds to a single inference. With advances today, it's down to 10 milliseconds. But using our sparse quantized model with the deep source engine, we're able to run it in sub 5 milliseconds on just a 4-core laptop CPU. What's great about this is we're able to take a model that was previously to run very quickly needed maybe like a server environment, right onto a reasonably sized on CPU. The other side of this, as we talked about, is actual size compression. Or models are getting larger. For example, the object detection model YOLO v3, which is very popular. The base version is 250 megs. BERT, off the top of my head, is maybe around 500. And these models get so large that they're not going to fit onto every single device that that engineers may want to deploy them on. So as an example, at YOLO v3, we're able to prune and quantize it. And with that, we're able to compress it by 16x all the way down to 15 megs. And if you are familiar with the YOLO family of models, of course, there's smaller versions that are might be more targeted towards edge deployments. But we can prune and quantize those even further, still for similar speedups and also space savings. Let's see, Mark, do you have any other questions?
Yeah, we had one more that came in, which was specifically asking about pruning and whether or not we can prune on GPU or CPU, and just the little bit more clarifications on devices that we can prune on, and both in terms of training and inference.
Yeah, definitely. So training wise, the process of pruning is what we call like a training aware process. So we start from a pre-trained model and we iteratively remove weights from it in a gradual manner while constantly retraining the weights. So you can think of it as just an extension to the already existing training process where weights at the end start to get removed. So for this to run efficiently, currently we still use we use GPU to train the models and make them sparse. Eventually we'd like to target sparse training as well. But for inference, once we have the sparse model, we're able to exploit a lot of properties of modern day multi-core CPUs to run efficiently for inference on CPU. Let's see, currently there are other there are some GPUs that support some structured forms of sparsity. Off the top of my head, like the A100s that have a certain sparsity pattern. And in terms of us for future hardware support, we are targeting, right now we work on modern Intel and AMD CPUs. And we're targeting, in the future, more edge-focused devices like ARM CPUs.
And then there was one more that was asking for clarification on quantization, if it was 8-bit integer or 8-bit float.
8-bit integer. Yeah, great. Yeah, so as an example, one of our recent projects we worked on was, as we mentioned, sparsifying of the YOLO v3 model. So YOLO v3, when it came out, was very exciting because it was one of the first models to provide a great trade-off between a good accuracy, but also being able to provide real-time inference performance on a decently sized GPU for the time. But since it came out, this full-size YOLO v3 model has not had great speeds on CPU, to the point where it's prohibitive to deploy YOLO v3 on CPUs. So we really wanted to focus on sparsifying and having great sparse performance of YOLO v3 on CPU to bring it to real-time object detection. So as an example, after creating the sparse YOLO v3, we took a 4-core CPU on a laptop and used it for run object detection on just a few scenarios around Boston. And you can see Mark and his dog are the star of the video. Let's see. Yeah, so while it's loading, yeah, one of the really cool things about it is it's running on a 4-core laptop. It's nothing fancy. It's $900 laptop. And again, we're going to be targeting even smaller devices in the future. You can see PyTorch is only able to achieve a very small amount of frames per second, and there's a noticeable lag in the frames update compared to the Neural Magic one, which is achieving this real-time in 20 frames per second. As a Zoom, you can definitely find this video on the homepage or yeah, and if you have any further questions, feel free to ask. But we also do have a blog post that goes in detail about what we did for this project and why it's interesting and how you can also apply it for your own object detection scenarios. Great. So how do we do all this, right? Because sparsifying, it involves a lot of different changes to, to maybe how you train models, how you export them. There's a lot of moving parts and pieces here. And even though it seems like this thing that's very very interesting, very exciting, why hasn't it been done more before? And it's because it's not necessarily an easy thing to do out of the box. And that's what our machine learning team is really focusing on, is an approach that'll make it easy to, one, apply these sparsification optimizations to your existing neural networks, and two, create new optimizations that can easily be plugged in. So we take what we call a recipe-driven approach, where the optimizations to be made are defined in these recipe configuration-like files, and the actual integration into your code should be as minimal as possible. So it's organized kind of in a three-tier structure, where the bottom line is these modifiers that are created to be generic algorithms that can run to sparsify, prune, quantize your models while training, and they run in a scheduled manner. But also modifiers can adjust other things in training too, like epoch, learning rate, regularization. And these modifiers, individually all can make an impact on your training flow, either to boost accuracy, to apply pruning or quantization. But it's still a lot to manage, which is why we have a manager object that wraps and groups the modifiers and just simply fits into your training flow to wrap optimizer steps, where these algorithms can easily be applied at the correct time. And then finally, recipe files are just simple human readable files. They're YAML based, where no additional code is needed, but you just define what optimization you need to add to your model, to your training flow, and then the manager takes care of the rest with just 2 lines of integration of code. And what we really focused on when developing the software was making it easy to integrate, so it can plug into your existing PyTorch training flow. And we'll talk more about it, and I'm definitely happy to answer any questions on it too. Some advantages of recipes include that it's very easy to track them through version control. As you're changing, you change hyperparameters in your model, you can track the, how you change the recipe very easily, whether this is changing how you do pruning, the learning rate, or more. And then if you need to add different optimizations to your recipe, rather than having to go into the code and changing, oh, let's add 30 lines of code to apply PyTorch quantization to our training, all we need to do is just add a simple modifier to our recipe. And there we can go from a base training flow to quantized training flow with just a couple lines in a recipe. All right, so I've talked a lot about recipes, but what does it look like? So like I said, it has a YAML syntax, and the modifiers are actually organized into functional groups. So there isn't a hard rule for this. Is more for readability, but anything stored in an object structure in YAML with the name modifiers is treated as a list of modifiers that should be fed to a manager. So in this recipe, we have training modifiers that say we should for 10 epochs with a learning rate of 0.008. So these are the base training modifiers. These are things that you'd have in your normal training flow anyways. And it's also optional, right? You can keep your existing learning rate structure, your existing epoch structure, but these are just additional is ease of use that you can use to augment your training flow. It's very easy to add in new learning rate schedules, especially to match your pruning and quantization schedules. So the next is pruning modifiers. We have a couple of different algorithms we use for pruning. This one in particular is global magnitude. What global magnitude does is it takes a sparsity target. Here it's 80%. And it prunes the model in a way such that on average across the model, 80% of the weights will become 0. Yeah, you can see that the modifier also is scheduled by start and end epoch. So the period in which it gets gradually pruned is starts at 0 and ends after the 8th epoch, with everything after that being held as recovery time, where the pruning structure stays, but no additional weights are pruned. Finally, another thing I like to point out about the pruning modifier is that we have a mask type, which can define forms of structure, non-structure, or semi-structure, where for sparse quantized models, we need the semi-structured block form, or we keep weights of groups of weights of 4 in a row at a time. And then finally, we have a section for quantization modifiers, where all we need to do to enable PyTorch quantization or training is simply one line for the quantization modifier and one line for the start epoch. There's options you can add as well, such as epochs at which like the quantization or which actually get quantized. Actually, for the pruning modifiers, we'll specify individual modifiers or individual layers that you want prune in your model. This is just an ease of use. This is just an ease of use token for running all layers in a model. Yep. And then finally, we have what we call a weight decay modifier, which disables L2 regularization after quantization has been applied, which we find helps boost the accuracy. Great. So this is overall what the recipes look like.
And we had a few quick questions that came in, Ben.
Yeah, definitely. It's a great time.
So one from Amir asking if we have to use a different learning rate and epoch settings, or if we can use the same ones from the original training run.
Definitely. So for epoch settings, the epoch range is going to depend on how long a specific model needs to recover from pruning, as well as how sensitive it is to pruning. The more sensitive a model might be to pruning, which depends on the structure and the nature of the weights of the model, generally the longer it may need to prune. And then for learning rate, generally starting at or maybe slightly above the final learning rate that your model was trained on is a good rule of thumb for starting pruning at. But to help with these hyperparameters, we actually have a UI that we've developed and are continuing to improve on, called Sparsify, that can create recipes for you while choosing good learning rates for your existing models.
Awesome. And then there's another question about can you integrate hyperparameter search with training modifiers? And then just kind of asking a little bit more on the intended workflow for being able to nail down hyperparameters that you would go through. And maybe you can dive in a little bit, Ben, into how we go through figuring out hyperparameters right now.
Yeah, definitely. So the first question there talks about hyperparameter search with the training hyperparameters. Right. So generally for epoch and learning rate, we don't have anything built in right now for hyperparameter search. It would have to be manual, but that's actually a great feature that we could think about for the future. Now for selecting so when we're just trying to sparsify a model, there's a few targets that we need to keep in mind. It may vary depending on your deployment scenario. And this is like the inference time of a model, like how fast does it take to run, the size of the model, what devices can it fit on, and finally the accuracy, or whatever your target metric is, which is how good do we want the model to be. And it's always going to be a trade-off between these three things. We can analyze a model for its loss sensitivity or its its accuracy or efficiency metric, that to see how sensitive the model would be to changes in pruning versus this loss metric. And we can also check the performance sensitivity, which is as we change the sparsity within a model, how does the performance change? And based on looking at trade-offs between these two things, we're able to figure out basically how do we want to prune the model in terms of hyperparameters there. And we can also do essentially like normal learning rate sensitivity analysis as well for choosing learning rate, except rather than starting from an unpruned model where we slightly tweak the learning rate until we see something that the loss responds to, we start from a trained model to see at what point do the weights start responding to a given learning rate.
Awesome, thanks, man. And then another question was just asking to go into a little bit more detail on the mask type and explain that again.
Yeah, definitely. So, you know, when I talk about pruning in the beginning of this demonstration or this presentation, we're largely talking about unstructured pruning, unstructured sparsity. And this is where any single weight in a model could be removed in a completely unstructured manner. This is actually you know, something that's pretty well researched, but in terms of deployment is fairly new. You know, where the deep sparse engine is able to take advantage of unstructured sparsity. But there's other forms of sparsity that are also you know, very well researched and used in deployment, such as maybe channel pruning, where entire channels within a layer are removed to actually make you know, that weight matrix smaller to get speeder that way, which is, you know, it becomes much more sensitive to, and you lose a lot more accuracy. But again, so kind of define what type of sparsity you would like to apply. In this case, 1-4 sparsity refers to a block sparsity structure that is required for sparse quantized models to work with the VNNI instruction set that that is needed to get the best performance from quantization. So what we're defining is on the output and input channels, how many values you want to group together in a block. So this 1-4 means we want to group in blocks of 4 on an input channel. So for quantization, for example, for this block pruning, like 0, 0, 0, 0, and then 1, 1, 1, 1, and then 0, 0, 0, 0 would be a structure where we have weights grouped in 4 in a row. And this will be valid for a prune quantized model. For unstructured, that might look something more like 0, 0, 1, 1, 1, 0, 1, 0, 1, something like that. You know, the ones and the zeros don't have any sort of structure between them. And we call this semi-structured pruning because it's less rigid than channel pruning, where entire channels may need to be sparsified at once. And it still you know, provides flexibility as long as things are grouped in these blocks of 4.
Awesome. And then there's one last question, which is, do you observe performance increases in smaller models?
Definitely. Yeah. So the performance, you know, can you know, mean multiple things. You know, on one end for performance, we're talking about you know, latency and throughput in terms of like inference speeds. And you know, we can see this in smaller models, especially when pruning to higher sparsities. But on the model structure and also how much we're able to prune. Interestingly, for performance as well, for like you know, your accuracy metric or your loss, pruning to lower sparsity actually can sometimes see in your accuracy or performance, where pruning kind of acts as regularization. You can kind of think of it to like a very aggressive dropout.
Awesome. And a few more that came in, but
Yeah.
I think let's go and move on to the next slide, and then we can answer those after that.
Yeah. Yeah. So this is just another quantization modifier. I've already been through this, so I'll just keep moving on. Yeah. So what can you do with sparse ML recipes? So we're constantly adding new modifiers, improving on our modifiers. But the great thing about these sparse ML recipes is that, like you saw before, the modifiers can be mixed and matched. A pruning modifier with a quantization modifier, we can create a sparse quantized model. But there's other things you can do as well. You can do sparse transfer learning, which is this concept we introduced where we hold the sparsity constant for a given model. So only the non-sparsified weights can get updated to take advantage of an existing sparsity structure we've learned for a new data set. And then just plain out of the box transfer learning, we have a modifier that makes it easy to do that called trainable parameters, where you can specify entire layers to freeze within your model. You can just fine tune an already trained model to a new data set. And finally, we also make it easy to set learning rate schedules. You know, a lot of training flows, you know, have a lot built into, you know, to control the learning rate. But with SparseML, it's easy just to define, you know, a simple YAML-based modifier that can do whatever learning rate schedule you may need, at least for common ones. And then, yeah, I guess, and then the cool thing about the pruning and quantization modifiers is it really takes these, you know, complicated processes that might not be so easy to use and makes it into, you know, simply, you know, 3 to 10 lines of YAML to define them. You know, because for sparsity, you know, it might add in, you know, a couple of hundred to 1,000 lines in your code base. Quantization word training in Python requires a lot of work that might not be, you know, that you might not be super aware of right out of the box, such as having to fuse layers in your model, having to define which layers to quantize, set up settings, propagate quantization configurations. So, you know, just with 2 lines, you know, you're able to enable these algorithms in your training flow. Right, so seeing all the things you can do with the recipes, the next thing I'd like to talk about is how do we actually apply them? Do you have any questions first, Mark?
Let's go through the application because the application will hopefully answer some of the questions. Yeah,
definitely. Yeah, so like I mentioned before, our team, we really focus on and pride ourselves in creating easy to use software. And what I mean by this is it should really only take 2 lines of code to do a bare bones integration of your training flow into SparseML. Right, so we have 1 line for importing. These are just defined things that you already should have in your training flow, such as your model and your optimizer for a PyTorch. And all we do is we load in the recipe to a manager object that we talked about before. And then we wrap your optimizer using the manager in your model so that at every step of the optimizer, we can look at the schedule for each modifier and run the algorithms that need to be run for pruning or quantization or learning rate updates. And then finally, your PyTorch training flow executes like normal, and SML comes in and makes updates along with your optimizer steps.
awesome. And then so some questions that came in. One was, can these recipes be used in PyTorch Lightning framework, or do they have to be used in plain PyTorch?
Right, so we haven't created a direct SparseML PyTorch Lightning integration. But essentially what we're aiming towards in the next update of our software is just to wrap anything with a step like structure. I know PyTorch Lightning has their fit function. So probably for integration, we'd have to go into the fit function and wrap their inner optimizer. But so basically in theory, it can be done. We don't have it set up today. If it's something you're interested in, it probably wouldn't be too hard to set up. You can definitely open an issue on GitHub and we can take a look more into it.
Awesome. And then there was another one, which was, is the sparse YAML file different for NLP versus vision-based models? And how can we create a YAML file that is that would be optimized for those different types of models?
Yeah, that's actually a great question. Let me go back here. Let's see. Right. So as we can see in this recipe, nothing here is actually model specific, which is great, which means it can be applied generally to any PyTorch model, with convolution or fully connected layers. What does become specific for models, though, is when recipes start to define individual parameters. So instead of saying all prunable here, we might name like 10 layers that we want to prune. So this would be different from NLP transformer-based model to a computer vision convolutional model. And the same goes for quantization. So, and then the next thing is that what could also be changed, obviously, is the way that these models are trained are different. So the learning rates might be different, the epoch range might be different, and the amount that we need to sparsify them also could be different. So I guess the two-part answer is, one, the structure of the recipe is not going to change. Where, both for computer vision and natural language processing, we want to set how we do the training. We want to define some way of pruning, and we want to define how we're going to quantize. And it's all the same modifiers. But what could change are the individual hyperparameters, which can be set with intuition from the domain you're working in.
Awesome. Let me just see if there are any that are relevant right now. And then another question is it assumed in the recipe that the sparsity that we are referring to is unstructured sparsity? And I think just a refresher on the other type of sparsity that we support through the library.
Yeah, definitely. So so in the beginning, we are assuming that we're talking about unstructured sparsity. And when we sparsify models without quantization, we generally target for unstructured sparsity. And the reason for this is because we can get to the highest levels of sparsity with the highest levels of accuracy recovery by having that unstructured nature without the constraints that you need to sparsify that way. The other kinds of sparsity that we support include channel pruning, which is where entire channels within a model are getting deleted. So instead of like a fully connected layer, having maybe 500 channels, or having a weight matrix like 500 by 500, we might sparsify out 30% of them and see speed up that way. Now for what we really focus on for prune quantized models, we have our semi-structured approach that we talked about, which is this 4-block pruning, where weights are pruned in groups of 4s. And this is so they can be fed into the vector instruction in a very specific way on the deep sparse engine side.
Awesome. And then one final one, just kind of building off of that, is, I think we might have lost Ben for a second. Ben, do we still have you there?
Hey, Mark, can you hear me?
Yep, there we go. Okay.
All right, great. Yeah, so did you hear what I was talking about for the block structure approach?
I think you cut off just at the end of it.
Okay, great. Yeah, and like I said, it's not as complicated as it may sound. It's literally just grouping weights that are 4 in a row and either keeping them all on or turning them all off. So 4 in a row that are kept, 4 in a row that are sparsified, 4 in a row that are sparsified, 4 in a row that are kept. So it's unstructured when you're looking at the scope of the 4 blocks. It's structured in the way that there need to be those 4 blocks, which is why we call it semi-structured.
Awesome. And then one additional question that builds off of that is, are different types of sparsification better suited to regularization versus reducing the size of models / speeding up inference?
Yes, definitely. I was kind of getting into before with this unstructured pruning versus structured pruning is that there's trade-offs. Right. So unstructured pruning gives you the most flexibility when pruning. So you can get the highest sparsity levels, 80 to 90%, with great recovery. For this channel pruning I talked about, the trade-off there is while you're able to take away large chunks of the model in a structured way that most engines can run once you process away all the sparsified weights, you're only able to get it to much lower sparsities, maybe 30, 35% without losing too much accuracy for a lot of models. So for the second part, in terms of inference, again, it really depends on your target hardware and the resources you have available. in terms of what you're going to pick. In general, though, unstructured is going to get you to the highest sparsities, which will get you the best speed ups, especially if you can run with a deep sparse engine.
So I think that's it for now.
Great. Yeah, so we're going to move on to the next section now, which is going to be a demo. Mark, you just let me know if you can see my tabs changing.
Yep, all good.
Great. Yeah, so I'm going to run you through a few Jupyter notebooks that are just looking at time, actually. I'll go pretty quick through them. But the idea here is I'm going to show you how we prune a Resident 50 model on a small data set, just integrating into a generic PyTorch training loop. So we can see the training loop we have here. We actually took it directly from the PyTorch website. And it, outside like a tiny change to work with our model, it's completely unchanged. Right, so we can integrate directly into it. We create our optimizer, our data set, and our loss function here. And we integrate into it just like we said before. We load a recipe, which is actually the exact recipe I had in the slides. And then we create our manager and wrap our optimizer. So we're trying to prune a model to about 80 to 90%. And we can just run our training loop. So all we're doing here is we wrapped our optimizer, and we're now calling into our training loop up here. And every time this optimizer.step is called, we're also calling into the manager behind the scenes, which controls the sparsity of the model. So this is actually going to run probably for about 10 minutes, so we're not going to watch the whole thing. But finally, there's a cell that was going to run the you check the model to see how much sparse each layer ends up being with the global sparsity. And then we have a ease of use function for exporting to Onyx. So Onyx is a universal neural network representation format, and it's what the deep sparse engine uses as input. So with that last export, we're able to run it in the deep sparse engine. Great. Yeah, so I think the big takeaway here is that almost everything in this entire notebook could just be a PyTorch training example. The only thing we really change is this one cell where we grab a recipe and then apply it. Everything else is unchanged from a normal training flow, and we're able to create a sparse quantized model. So finally, the last thing I want to show is just given a sparse model, how it performs to dense on some target hardware. So this is a 24-core CPU running in AWS. It has VNNI instructions, so we can run quantize. And we're just going to run through a few deployment scenarios on it. So with the deep sparse engine, we can always restrict the number of cores and the batch size we run on. So this is the 4-core batch size 1 scenario, which kind of represents, real-time latency, on laptop, like we did for the YOLO example. So this is that same resident model. I just trained it up last night, and we're just going to see how it ended up performing. This is a benchmark function, just using some tooling that dsparse provides. And then we can run first the dense model. So we see we got 58 images per second here. And then we can run the sparsify model, which is prune and quantize. And you see we got to 236 images per second. You can see that's a 4x speed up. We can actually get to 5x. Often it depends, on maybe other resources that are being used, or actually how sparse the model got. I think this model is pruned to 80%, so it definitely could get larger. Other deployment scenarios we could try could be like for a high throughput scenario, where we use all the cores on the server for a large number of batch sizes. And then one cool property of running on these CPU servers, with sparse models that can run efficiently compared to GPUs, we can get much higher batch sizes through, since we have access to more memory, as opposed to what like a single GPU might have. We'll run again. These will take a little longer, so while these are running, I am definitely open to any question that might come up in the rest of the time.
Oh, I'm muted. There we go. So we have a few questions coming in. And one of them was, any thoughts on why NVIDIA chose to support structured sparsity rather than unstructured, if unstructured can give the most speed up?
Yeah, I think a lot of that has to do with their with the actual devices and the way they're set up. I haven't looked too much into the latest architectures, but definitely it's very amenable to their current GPUs and the way the cores are set up. I do think they are working towards unstructured in the future, as far as I'm aware. But yeah, so the 2-4 structure, I would say, is not quite, it's definitely very structured, especially compared to the block structure of this 4 block that we have. It's not the same thing when you think of a 4 block. But it is a good step in the right direction for models in general becoming more sparse. And sparse ML is definitely something that could be used to create these kinds of sparse models, right? It's not just to create models for CPU inference. Any sort of sparsity you want to target, these models can be done with sparse ML.
Yeah, and we should also mention that there is some research out right now that is looking at running unstructured sparsity on GPUs. It's still in very, very early stages, but they did show that that at least it was possible to run on the NVIDIA GPUs with unstructured sparsity. So we're definitely interested in seeing how that works out as well.
Yep. And then so we can see we got a 5.72x speed up here, which is great. One thing I would like to point out is that we're comparing against the deep sparse dense versus deep sparse sparsified, where the deep sparse engine already has a lot of optimizations in there for applying certain types of convolution operators that make dense inference much faster than it would be out of the box on PyTorch, which is why we saw close to 10x speedups versus PyTorch CPU in our YOLO example, whereas here it's closer to 5.7 since we're running both on deep sparse.
Awesome. And then another question coming in, just talking over kind of deployment. There were a few questions that came in over deployment and then deployment file types. So specifically, someone was asking about the torch.jit library. Why can't we just use the torch.jit library for moving the final model to deployment? And then there was also a question on, can you take the Onyx file to TensorRT?
Yeah, definitely. So first for torch.jit, the SparseML isn't targeted just towards PyTorch. We actually can sparsify models in Keras and TensorFlow as well, and we'll have future demonstrations of how to do that. But for reading from dsparse, we read from the Onyx file, which isn't tied to how the operators or forward passes are set up in torch.jit, and instead can be defined just through the Onyx proto file. We're definitely looking to make it easier to load natively from like a torch.jit file and just export behind the scenes into Onyx. That's something you could look out for maybe in the future. And now and the other one was TensorScript, TensorRT.
TensorRT, yep.
TensorRT, yeah. Yeah. So for TensorRT, we don't provide any of our own native what's it called? Any of our own native conversions from Onyx to TensorRT, but I think there are some that can be installed if you're interested in using our sparsify models on TensorRT.
Yeah, the process.
In general,
I was just say the process isn't the most fun thing, but TensorRT is getting better at being able to convert from more models, and they do have some tutorials that walk you through converting from an Onyx file.
Yeah, definitely. So if you can go from Onyx to TensorRT, then you can use our sparsify models with TensorRT essentially.
Yeah. And then let's see, there was. There was a quick question on just going back to structured versus unstructured sparsity, if there was any benefit with any in all caps for using structured sparsity rather than unstructured sparsity.
Definitely, yeah. So the traditional reason why people went for structured sparsity is that it's just easier for other engines to deploy, right? Just say it's like PyTorch out of the box or Onyx runtime where they might not necessarily have, I don't know what they have today, with them having the passive unstructured sparsity kernel. What you can do is if you can, do a channel pruning where you're deleting an entire row, the parameter just becomes smaller, so it can just run on a smaller matrix multiplication. You can get speed up that way.
Definitely.
And that would be the main benefit. But again, you're not getting anywhere near as high sparsity, and the speed will likely be less as well.
Yeah. And there's an interesting point to add on to that, which is that if you take a structurally sparse model and train that from scratch again, it will recover to, there's a few papers out that recover to right around the same level as the baseline model if you had just trained the original baseline model structure pruned. But we don't see the same happen for unstructured sparsity, which is very interesting. So there's also, to Ben's point, the accuracy difference can be very large due to these kind of weird phenomena that are happening in the deep learning space as well. And then there's a question on inducing activation sparsity and if the tooling can be used for that.
Yeah, so the tooling definitely can be used for that. We have documentation for it, and can definitely put out a tutorial for how to do it as well. It's essentially just switching out the activation function you use to have a filter that adds an activation sparsity. Yeah, Mark, correct me if I'm wrong, I think the modifier, we don't have it today.
The modifiers, so 2 different modifiers that we have in the PyTorch framework right now. We don't have anything for TensorFlow or Keras though. But the two are, there's one for activation regularization, and then one for what we call fat ReLU, which forces, as Ben said, forces the activation threshold higher. So both can be used in combination to create more sparse activations for models. And then let's see. There's a question on the cuSparse kernels, specifically talking over the sparse kernels that are supported through the CUDA libraries, and any comments on why there are no inference runtimes that take advantage of the cuSparse kernels for unstructured sparsity.
Yeah, I'm not too familiar with cuSparse itself. I don't know, Mark, if you have more comments about this one.
Yeah.
But, yeah.
Yeah, I can jump in on this one. So what's interesting is that, I mean, there are a few comparison papers that walk through the cuSparse kernels and the libraries. Because of the way that the code is structured there for unstructured sparsity, and because of how the data has to move across that to actually get speed up in the cuSparse kernels, you need to be around 99% sparse or sparser. And there was, so we can link out to the paper that, this is a paper I was talking about that was comparing unstructured sparsity on GPUs. And that was diving into specifically speeding up the convolutions that are happening there. But net, because of the implementations of the cuSparse kernels, anything less than 99% sparse, unfortunately doesn't see any speed up due to the inefficiencies in how the algorithm was implemented. And these are, it's not necessarily just, issues with the code and it's easy to fix. It's a very hard problem to actually structure the compute such that you'll get speed up, because obviously you don't have to run the zeros, but that also still means a lot of data movement and you're moving a lot of stuff across caches and things like that. So cuSparse kernels don't work well for anything other than highly sparse kernels, and that's generally why it's not used in the deep learning space, because getting to above 99% sparsity is generally cuts out too much information from these networks to make them useful in deployments.
Great, thanks, Mark.
And yep, so that is just a clarification real fast that the cuSparse library would be for unstructured sparsity. And they had the right intuition, which is that structured sparsity can't reach 99%, right? And yeah, that would be a very small model that would not do very well. Okay, and then let's see.
Oh, we have a question about NLP models. Yeah, so NLP is currently a big target for us. We do have some code up. You can check in our integrations library about integrating the Hugging Face for sparsifying their models. And we'll be having support for that as well for sparse quantization in the near future. So definitely keep an eye out for that. see. So we have 2 minutes left. So I just wanted to quickly go through a slide on our citations of things that help with the presentation. And then definitely I encourage everybody to check us out on GitHub. Give us a star if you like it. If you have any issue with it, please or have any feature requests, raise issues, submit pull requests if you have any pull extensions or examples. And then connect with us on Slack and Discourse from neuralmagic.com/community. We're very active in those channels, and it's a great way to reach out to the developers just to talk about the space. And if you'd like to reach out to me personally, you can send me an email, just ben@neuralmagic, reach out on LinkedIn or GitHub. Just drop me a line and let me know what brought you to the presentation today and why you're interested in Sparsification. Would really love to hear about it. You can definitely chat. So, Mark, do you have time for a final question?
Let's see. There were a few questions on deep reinforcement learning and the ETA on when we might have that.
Right. Yeah. So reinforcement learning is a domain we haven't really gone into yet. It's definitely possible to sparsify these models with our software, but just in terms of targeting for the deep sparse engine, that depends on a lot of times on market needs and what will be on our roadmap. I don't know if you have any other thoughts on that, Mark.
Yeah, it's in our medium to long-term roadmap right now, as has been said. We don't have exact timelines right now, mainly just focused on vision and NLP. But we are very excited on the potential work there that can happen with reinforcement learning and even GANs and stuff. Some of the kind of more edge use cases are definitely really exciting that we'd like to look into in the kind of medium to long term.
Definitely. And then optimizer type. Yeah, generally what the model is trained with, Atom will obviously converge faster, but SGB could be better for pruning since it, since when we have more steps, we're able to drag out the pruning a little bit longer. But yeah, we've used both. Let's see, Stanford sparse DNN. Is this the project that came out? Which one this is, Mark?
Yeah. It came out earlier this year to the end of last year, but it's definitely something that we're keeping an eye on. It's very interesting research that built on top of the research that we're doing right now. So definitely keeping an eye on it to see how much speed up they're achieving and doing active comparisons with it. In general, they don't have a product out for that or anything like that. So it's one of those things that comparing research numbers to productized numbers is a bit tricky because you can simplify models down such that you only have a very set list of operators that are running, and that's essentially what they're doing in that paper. So they're along the right threads of what we're doing internally. But there's still a lot of pieces missing from being able to make that into an inference engine that you would be able to ship.
Great. Yeah. Let's see. Oh, we do have one more question, which is what is the basis behind the projection accuracy recovery confidence in the Sparsify tool? So let's see. So this question refers to Sparsify, which is what I mentioned is our UI for creating recipes, from your existing models. And part of the model is going to recover well given the current recipe. Right. So the sensitivity analyses are based on common, things I've been studying literature before for sensitivity for pruning. And then for the actual confidence, this is just derived from that. I don't know if this came from a paper or not, Mark.
No, not from a paper. It's from our internal research. Yeah.
So just for internal research, but this is something we actively work on, and we'll definitely publish more results about in the future.